Outside a spacecraft, an object in direct sunlight can face temperatures around 250 degrees Fahrenheit, while a similar object in shadow can fall toward 250 degrees below zero. Same orbit, same vacuum, same sun. A swing of roughly 500 degrees across the difference between light and shade. Stop on that for a moment. The temperature does not slowly fade from hot to cold across the gap. There is no gradient of warm air thinning out into colder air. There is just sunlight on one side and shadow on the other, and the difference between them is roughly the temperature difference between a working oven and a hard winter night in Siberia, right next to each other, with nothing in between. Most of us picture space the way we picture a freezer, cold like a place. Cold is a temperature you could fall into, the way you fall into cold water. We grew up imagining space as a place that instantly turns anything into ice. That is not what space is. Space is not cold the way a freezer is cold. A freezer is cold because it is full of slow air, and that air is touching you everywhere at once, and it is patiently pulling the warmth out of your skin. Space is something else entirely. Space is almost empty, and what we call its temperature turns out to be a question with at least 6 different answers, depending on what you mean by the word. Tonight, we walk slowly through all 6. A window in winter, the sun's strangest mystery, the one where heat seems to be moving the wrong way, and the oldest light still arriving from the first quiet moments of the universe. We begin. Before we get anywhere near a spacecraft, or the sun, or anything cosmic at all, the word cold needs to start somewhere familiar. It needs to start in your body, in your room, in something you have actually touched. Picture a window in winter. The room is warm. The heater is humming somewhere in the wall. You walk over to the window and you put the palm of your hand against the glass. What you feel almost instantly is cold. A cold that seems to move into your hand from the glass. A cold that feels like it has weight to it. Here is the first quiet trick the word cold plays on us. The cold did not move into your hand. Nothing moved into your hand. What actually happened is the opposite. The warmth of your hand started leaving. The glass is at a lower temperature than your skin, and when two things at different temperatures touch each other, heat always flows in the same direction, from the warmer thing to the cooler thing, from your hand into the glass. That is what cold actually is, in the everyday human sense. Cold is not a substance that pushes into you. Cold is what you feel when warmth is being pulled out of you. Let that sit for a moment, because the whole script depends on it. There is a quiet experiment you can do without leaving your chair. Imagine 2 floors in the same house. A wooden floor in the bedroom and a tile floor in the bathroom. Both rooms are heated to the same temperature. Both floors are sitting at, say, 68 degrees Fahrenheit. Now take off your socks and step from the wooden floor onto the tile. The tile feels much colder, almost shockingly colder. Even though a thermometer would tell you the 2 floors are at exactly the same temperature. The thermometer is not lying. Your foot is not lying either. They are measuring different things. The thermometer is measuring a number. Your foot is measuring how quickly heat is leaving it. Tile pulls heat out of your skin much faster than wood does. The molecules in tile are packed in a way that lets vibration travel through them efficiently, the way a vibration travels easily through a metal rod and barely at all through a wool sweater. So when your warm foot meets the tile, the warmth flows away from you quickly. Your nerves register that fast loss as cold. On the wooden floor, the warmth leaves much more slowly. Wood is full of tiny pockets of air and slow, disorganized cell walls. The vibration of heat cannot pass through it easily, so your warmth stays close to your foot longer. Your nerves register that as warm. Same temperature. Different speeds of heat leaving you. 2 completely different sensations. This is the first rung of the ladder. Cold, at the human scale, is not a thing the world has. cold is something your body does when warmth flows out of it faster than warmth flows in. Now hold that thought, because it is about to do strange things to everything else we look at tonight. Because if cold is really just warmth leaving, then the question, why is space cold, becomes a very different question. It becomes instead the question of where the warmth would go. And what, if anything, is there to take it? In the room you're in right now, your body is at about 98 degrees. The air around you is at maybe 70. Your skin is constantly, quietly losing warmth to the air, and the air is carrying that warmth around the room. Some of it brushes against the cold window and slows down. Some of it rises near the heater and speeds up again. Your body is in a slow, invisible conversation with the room, trading heat back and forth, and the conversation is what keeps everything in the room roughly stable. Now imagine just for a moment that you took the room away, not just the walls, the air too, every single molecule. You leave your body floating in nothing. Your body is still at 98 degrees. Your body is still trying to lose heat to the world around it. But there is no world around it to trade with. There is no air to carry warmth away. There is no glass to pour warmth into itself. There is just you and the empty space and nothing in between. What happens next is the question this entire script is about, and the answer turns out to be much stranger than anyone's first guess. Settle in. We are walking toward the heart of it. Heat does not just exist in a place. Heat moves. It is always moving, all the time, from anything warmer to anything cooler nearby. And the strange thing about heat is that it has exactly 3 roads it can take to get anywhere. Just 3. That is the whole map. Once you understand those 3 roads, almost every cold thing in the universe starts to make sense, including the cold of space itself. The first road is called conduction. Conduction is the road heat takes through touching. 2 things at different temperatures press against each other. Their molecules meet at the boundary, and the faster jiggling molecules nudge the slower ones until they speed up. The warmth spreads across a handshake. This is what happens when you hold a mug of hot tea. The mug is warmer than your hand. The molecules at the surface of the mug are jiggling fast. They bump into the molecules of your skin, and your skin starts jiggling faster too. After a few seconds, your hand feels warm. That is conduction. A long chain of tiny handshakes passing the warmth along. Conduction needs something to touch. It does not happen across empty space. If you held the mug an inch above your palm, your hand would feel almost nothing from it, even if the mug was steaming. That is the first road. The second road is called convection. Convection is the road heat takes through a flowing fluid, whether that fluid is a liquid or a gas. When you turn on the heater in your room, the air right next to the heater warms up. Warm air is lighter than cold air, so it rises. The rising warm air pushes the cooler air down toward the floor, where it gets pulled back toward the heater and warmed up in turn. Pretty soon the whole room is in motion. Warm air going up, cool air coming down, a slow, invisible river circulating through the space, evening the temperature out. That is convection. Heat carried by the bulk movement of a fluid. Convection is how a pot of soup heats evenly on the stove. It is how the wind carries the warmth of a summer day across a field. It is how your body sheds heat into the room around you on a hot day. Convection needs a fluid to flow. Without a fluid to move, convection cannot happen. That is the second road. 2 down. The third road is called radiation. And radiation is different from the first 2 in a way that turns out to be the most important fact in this entire script. Radiation does not need anything in between. When you stand near a campfire on a cold night, your face gets warm, even though the air between you and the fire is cold. The warmth you feel is not coming through the air. It is coming through light. Not light you can see exactly, but light just below the visible range. Light called infrared. The fire is so hot that it is glowing in infrared, and that glow is traveling outward in every direction, and some of it lands on your face and is absorbed and felt as warmth. That is radiation. Heat carried by light, heat that can cross any gap that light can cross. And light can cross anything. Light can cross your room. Light can cross an empty bottle. Light can cross 100 miles of empty air. Light can cross 93 million miles of nothing between the sun and your skin. So here is the map, all three roads laid out together. Conduction needs touching. Convection needs a flowing fluid. Radiation needs neither. Radiation can cross a vacuum. Now think about what space actually is. Space is the absence of almost everything. There is almost nothing to touch. There is almost no fluid to flow on padded it. Two of the three roads are completely closed in a vacuum. Conduction cannot happen because there is nothing for warmth to pass through. Convection cannot happen because there is no air, no water, no fluid of any kind to circulate. Only radiation works. That single fact is doing more heavy lifting than any other sentence in this entire video. Let it sit. Two of the three ways heat can travel are simply not available in space. The road from the sun to the earth is a vacuum, and the only thing that can cross it is light. So when the sun sends out enormous amounts of energy, the energy is traveling as light. It crosses the empty space between us and the sun without warming that space along the way. The empty space cannot absorb the light because there is almost nothing there to absorb anything. The light just passes through, like a thrown ball passing through an open doorway. The doorway does not catch the ball. The light does not warm the road. Only when the light meets something solid does the warming actually happen. When sunlight lands on the side of a spacecraft, the metal absorbs the light and heats up. When sunlight lands on your skin through a window, your skin absorbs it and warms. The energy is real. The warmth is real. But the warmth shows up only at the destination, not on the road that got it there. Hold that picture, because this is the central trick of the whole title. The sun is screaming. The space between the sun and us is screaming with light, full of energy in transit. But the space itself does not get warm. The light is just passing through. That is most of the answer to the title right there. But it is only half of it. The other half is much stranger. Because the question is not just, why doesn't the road warm up? The question is also, how cold can the road actually get? And once we get there, the answers start to bend in ways that are genuinely hard to picture. We will get to that. First, we should look at what happens at the destination, the place where the light finally arrives, and what it actually does to the metal it lands on. Outside a spacecraft in low Earth orbit, an object in direct sunlight and the same object in shadow, considered temperatures roughly 400 or 500 degrees apart. NASA estimates the extreme spacewalk suits must protect against at about plus 250 degrees Fahrenheit in sunlight and minus 250 degrees in shadow. That is the working environment. That number is worth pausing on. A 500-degree spread across the width of a body. The same vehicle, the same minute, two surfaces almost touching each other, separated by the difference between an oven set to broil and a freezer that could not exist anywhere on Earth. This is what the title is pointing at in its most physical form. Anything caught between sunlight and shadow in space lives in both worlds at once. Now think about what this means for the people who actually build spacecraft. Imagine you are an engineer at NASA or at the European Space Agency or at any of the smaller spacecraft companies that have started up in the last 20 years. Your job is to keep a piece of equipment alive in this environment, not for a few minutes, For years, sometimes for decades, you have a satellite that you are about to launch. The satellite has electronics inside that have to stay at roughly room temperature. Too hot, and the circuits stop working. Too cold, and the lubricants in the moving parts seize up. The batteries lose their charge. The metals contract and stop fitting together. Your satellite has to live in a place where the temperature swing is bigger than any spread that has ever existed naturally on Earth. And the swing happens every 90 minutes as the satellite passes from sunlight into Earth's shadow and back out again. How do you keep it alive? The answer is one of the quietest pieces of engineering in modern history. It is called multi-layer insulation, often just abbreviated as MLI. If you've ever seen a photograph of a spacecraft, you've probably seen it without knowing what you were looking at. That golden, crinkled foil-looking surface that wraps so many satellites and probes is not paint. It is not a single shiny sheet. It is many layers of reflective films and fabrics, often aluminized materials, laid one on top of another, with tiny spaces in between. Each layer is so thin that you could crumple a square meteorite into the size of a fist. And the whole stack, sometimes 10 layers, sometimes 20 or more, is doing one specific job. It is making radiation, the only road heat can take in space, work as poorly as possible. Here is the trick. Each reflective layer sends most of the infrared radiation back the way it came. The small amount that gets through meets another layer, then another, then another. By the time heat has crossed the stack, the radiative road has become slow enough for the spacecraft to survive. The end result is a wrapper that lets a spacecraft in full sunlight hold on to enough warmth inside itself to keep its electronics alive. And, in full shadow, lets it bleed warmth away so slowly that the inside stays survivable. The same wrapper does both jobs. Because radiation is the only road, and the wrapper just makes that road harder to travel. And even that is not enough on its own. Spacecraft also have heaters, strips of resistance wire built into critical components, switched on whenever a sensor reads that a part is getting too cold. They have radiators, the opposite of heaters, flat panels designed to glow brightly in infrared so they can shed warmth out into the cold of space. A satellite is a balancing act, constantly trading heat back and forth between sunlight, shadow, electronics, and radiators, kept inside a narrow temperature band by all of these systems working at once. For most of the spacecraft we have ever built, this works. It is one of the quiet, daily miracles of modern engineering. The James Webb Space Telescope took it to an extreme. Webb's instruments need to be so cold to function that the entire telescope sits behind a 5-layer sun shield the size of a tennis court. The sun shield blocks the sun and lets the back of the telescope drop to around 50 degrees above absolute zero, naturally, just by hiding from the sun in a corner of empty space. That is one of the most extraordinary sentences I know how to write. We built a thing that is colder than anywhere on Earth, simply by giving it a shadow. You can do the same trick yourself with a parked car on a summer day. Park in direct sun, and the dashboard becomes too hot to touch. Move the same car 20 feet into the shade of a tree, and within an hour, the dashboard is cool. The car did not change. The sun did not change. Only the road between them changed. The road got blocked. Webb is doing that on the largest possible scale. It is parked in the shadow of its own umbrella, 1,000,000 miles from Earth, and that shadow is enough to lower its temperature into a range where it can see things no human-built telescope has ever seen before. So when we ask why space stays so cold if the sun is so hot, this is one of the clearest answers. Space by itself is in shadow. Even when sunlight is pouring through it, space is not the destination. Space is the corridor. Everything the light passes through has nothing to absorb the light, and almost nothing to be warmed by it. And so the corridor stays as cold as it would be if there were no sun at all. Only the things in the sunlight get warm. Only the things in the shadow stay cold. And in space, the difference between sunlight and shadow is just a few feet of nothing. We are about to scale this up. Because the same thing that happens across a spacecraft also happens across an entire world, when that world has no atmosphere to soften the swing. If this quiet walk through space and temperature is the kind of thing you like at night, subscribing helps more of these slow science journeys reach the right people. Now let's go one layer deeper, because the sun itself has a temperature problem that still has not been fully solved. The moon is the closest world we have ever set foot on. 12 human beings have walked on its surface, the last of them in 1972. All 12 of them landed on the side of the moon that faces the sun at the time of their landing, and they did their work in lunar daylight, and they left before lunar night arrived. There is a reason for that. The moon has no atmosphere, none, no air, no water vapor, no clouds, no wind, nothing that can carry warmth from one side of it to the other. And without an atmosphere, the moon experiences something the Earth never does. The lunar surface can heat to about 260 degrees Fahrenheit, around 127 degrees Celsius, in direct sunlight. And it can cool to about minus 280 degrees Fahrenheit, around minus 173 degrees Celsius in the long lunar night. That is a swing of roughly 400 degrees on the same grey dust where Aldrin and Armstrong stood. Same surface, different time of day. The lunar day, by the way, is not what you might think. A point on the moon's equator sees the sun rise, climb across the sky, and set over the course of about 2 Earth weeks. The night that follows is another 2 Earth weeks long. Daytime on the moon is not measured in hours. It is measured in fortnights. Think about what that means for the rocks on the surface. A patch of dust at lunar noon has been baking in continuous direct sunlight, with no air to carry the warmth away, for the better part of a week. The light has been pouring in. The rock has been absorbing it. Radiation, the one road that works in a vacuum, has been delivering heat to the rock with no convection or conduction to spread it around. And then the sun sets. Slowly. Over the course of hours, the patch of dust is now in shadow. The light stops arriving, and the rock starts to do the only thing it can do in a vacuum, which is to radiate its warmth back out as infrared light into the empty sky. There is nothing to slow this down. There is no blanket of air to hold the warmth in. There is no body of water nearby to soften the swing. The rock just glows softly in infrared, hour after hour, sending its day-long pile of warmth back into the dark. By the time the long lunar night reaches its middle, the rock is colder than anywhere on Earth has ever been measured. And here is the strange part. The temperature in some lunar craters at the South Pole, places where the sun has never actually risen because the geometry of the moon keeps them in permanent shadow, has been measured at around minus 4,010 degrees Fahrenheit. Even colder than the lunar night equator. Some of the coldest places in the inner solar system are not in deep space at all. They are at the bottom of small dark holes on a world we can see in our sky. And here is the strange part. These craters are colder than the surface of Pluto. Pluto is 40 times further from the sun than the moon is. And yet Pluto's daylit surface is not as cold as the floor of a permanently shadowed crater on the moon. Why? Because Pluto, despite being so far from the sun, has a thin atmosphere of nitrogen that smooths out its temperature a little. The moon's craters have nothing at all. That is the lesson of the moon, written across an entire world. Where there is no atmosphere, there is no smoothing. The day is brutal and bright. The night is brutal and dark. The places that never see the sun are colder than worlds, an unimaginable distance further out. The road from the sun is just light, and where the light goes, things get hot, and where the light does not go, things get cold beyond anything you would expect. There is no in-between on the moon. There is sunlight and there is shadow, and the temperature difference between them is a 400-degree wall. On Earth, this is invisible to us. We never feel it, because Earth has its atmosphere, and the atmosphere is one of the great quiet engineers of comfort in the solar system. Our air carries warmth from the day side of the planet to the night side. Our oceans store heat from summer and release it slowly through winter. Our clouds reflect some of the sunlight back into space and trap some of the warmth before it can leave. We live on a world that has hidden the brutality of the sun vacuum interface from us so thoroughly that we forget the interface is even there. The moon does not hide it. The moon shows you what the question, "Why is space so cold?" really looks like when you take away the cushion. And the answer is simple. The sun heats the things it lights up. The shadow cools the things in shadow. The road between them does not warm up because the road is empty. And without an atmosphere to soften the edges, the two sides of that wall sit 400 degrees apart, and you walk from one to the other in a single step. There is more here. We have been talking about temperature as if it is just a number. And it is. But what is the number actually measuring? It is not measuring what you think. Here is the question almost no one stops to ask. When a thermometer reads 70 degrees Fahrenheit, what is the thermometer actually counting? Not the abstract idea of warmth, not some property of the air as a whole, not a feeling. The thermometer is counting something very specific. It is counting how fast the molecules around it are moving. Temperature, in physics, is just the average kinetic energy of a bunch of particles. Kinetic energy is a fancy word for motion. So when you measure the temperature of the air in your room, what you are really measuring is how energetically the nitrogen and oxygen molecules around you are bouncing around. A warm room has fast jiggling molecules. A cold room has slow jiggling molecules. That is the entire definition. This is one of those facts that, once you really understand it, changes how you think about almost everything else we have been walking through. Think for a second about what a breath actually is. It is a small crowd of molecules, all moving at high speed. At room temperature, the average nitrogen molecule in your lungs is moving at something like 500 meters per second, which is faster than the speed of sound. They are bouncing off each other, off the walls of your lungs, off the inside of your nose. They are zipping around so quickly that if you could see one, it would streak past your eye in less than the time it takes to think the word streak. That motion is the warmth of your breath. The faster they move, the warmer it is. The slower they move, the colder it is. Absolute zero, the coldest temperature physics allows, is the temperature at which molecular motion has slowed down as far as it can possibly slow down. Not stopped completely, because quantum mechanics does not let anything be entirely still, but slowed to the absolute floor. Absolute zero is 0 Kelvin, which is about minus 273 degrees Celsius. It is the lowest temperature that anything has, anywhere in the universe. Now, here is the move that reframes the entire script. If temperature is the average motion of particles, then in order to have a temperature in the everyday sense, you need to have particles to count. You need a crowd. What does it mean to ask for the temperature of a place that has almost no particles in it? What does it mean to take a thermometer and ask it to read a vacuum? The honest answer is the thermometer will give you a number, but the number is not measuring what you think it is measuring. The thermometer is not measuring the vacuum. The thermometer is measuring itself in equilibrium with whatever radiation happens to be hitting it. Think of it like this. Imagine you have a normal kitchen thermometer and you stick it out into a room. The thermometer is in contact with a crowd of air molecules, all of which are jostling against the bulb. They are passing their motion into it or absorbing motion out of it until the thermometer and the air are jiggling at the same rate. When that settles, the thermometer reads the temperature of the air. Easy. Now take that thermometer to a place where there are almost no particles. The thermometer is no longer surrounded by a crowd to settle into. It is just sitting there, alone, in a near vacuum. There is no air to nudge it. What it does instead is feel the light. Photons of light come in from every direction. Some are from the sun, if the thermometer is anywhere in sunlight. Some are very faint photons of background light from the rest of the universe. The thermometer absorbs the ones that hit it. It also gives off photons of its own in infrared. When the photons coming in match the photons going out, the thermometer reaches an equilibrium temperature. And that temperature has very little to do with the few stray particles around it. It is mostly about the balance of light. This is why a piece of metal in direct sunlight on the moon gets to plus 107 Celsius, while a piece of metal 100 meters away in shadow drops to minus 173 Celsius. The two pieces of metal are sitting in roughly the same vacuum. The vacuum has the same density in both spots. But the light balance is completely different. One is being showered with sunlight. The other is being showered with nothing but the cold infrared glow of the deeper sky. The metal does not care about the vacuum itself. The metal cares about the photons. So when we ask, what is the temperature of empty space, we are asking a question that has a strange answer. Empty space does not really have a temperature the way your kitchen does. Empty space has a radiation environment, and anything you put into that environment, if you let it sit long enough with nothing else around, will settle to a temperature determined by whatever light happens to be hitting it. In sunlight, that temperature is hot. In deep shadow, that temperature is cold. In the truly empty places, far from any star, that temperature is colder still, but never quite all the way to absolute zero. Because the universe is not perfectly dark, there is a faint glow that comes from every direction, in every part of the sky. No matter where you look, we will get to that glow in a little while. For now, this is the reframe. Temperature is what matter does when it is jiggling. Space is mostly not matter. So when we say space is cold, what we really mean is something more careful. We mean that there is almost nothing in space to be hot or cold in the usual sense, and that anything we put into it will lose more warmth to the dark sky than it gains from the dim background, unless it happens to be standing in a beam of sunlight. Cold, at the human scale, is warmth flowing out of you. Cold in space is radiation flowing out of you with almost no radiation flowing back in. Same idea, scaled up to the size of the universe. And once you carry that picture into the next section, the sun starts to do something almost no one expects. Because the sun, the source of all that warmth, has a strange problem in its own atmosphere, a problem that physicists have been quietly puzzling over for nearly a century. A problem where heat appears to be moving the wrong way. The surface of the sun, the part we can actually see when we look at it with proper filters, is called the photosphere. The photosphere has a temperature of about 5,500 degrees Celsius. That is the source of the light that warms your skin on a summer afternoon. It is the source of the photons that have been crossing 93 million miles of vacuum to land on every cold rock and warm spacecraft we have looked at so far. Keep that number close. 5,500 degrees Celsius. The surface. Above the surface of the sun, there is a thin region of much, much hotter gas called the corona. The corona is what you can see during a total solar eclipse, the pearly halo that surrounds the dark disk of the moon when it covers the sun's bright face. The corona is faint compared to the photosphere, but it is enormous, extending out from the sun for millions of miles. And here is where the strangeness begins. The corona, which is further away from the sun's core than the photosphere is, has a temperature of around 1 to 3 million degrees Celsius. Read that again, because it is worth reading twice. The sun's core is hot, naturally. The surface, the photosphere, is 5,500 degrees. The thin gas above the surface, further out from the core, is over 1,000,000 degrees. That should not happen. That breaks the most basic intuition you have about heat. If you walk away from a campfire, you expect to get colder. You expect the heat to fade as you move away from its source. You do not expect to walk further from a fire and suddenly find yourself in a region 100 times hotter than where you started. That would break every intuition you have. But that is what is happening on the sun. The corona, sitting further out, is somehow hotter than the surface beneath it by a factor of about 200. The science of how this happens is called the coronal heating problem. It is one of the oldest unsolved questions in solar physics. Astronomers have known about it since the 1940s, when they first carefully measured the temperature of the corona during eclipses and realized the numbers were wildly higher than the surface. There are theories. There are good theories. We do not have a final answer. The two leading explanations are both being actively tested right now. The first is something called wave heating. The idea is that the sun's surface is constantly bubbling and shaking, the way the top of a pot of boiling water shakes. That shaking sends waves of energy upward into the corona, the way ripples spread out from a stone dropped into a pond. By the time those waves reach the corona, they have built up enough energy to heat the thin gas there to extreme temperatures. The second is called nano-flare heating. The idea here is that the sun's magnetic field, which is a tangled and chaotic thing, is constantly reconnecting and snapping in tiny, invisible events. Each event releases a small burst of energy. The corona is being constantly peppered with these tiny snaps, like 1,000,000 quiet firecrackers, going off every second, each one heating the gas a little more. Probably the answer is some mix of the two. Probably there are details we have not yet found. In 2018, NASA launched a mission specifically designed to fly closer to the sun than anything has ever flown, on purpose, with the goal of measuring what is actually happening inside the corona. The mission is called the Parker Solar Probe. It is named after the physicist Eugene Parker, who first predicted the existence of the solar wind back in 1958. The probe is wrapped in a heat shield made of carbon composite, designed to handle temperatures over 1,000 degrees Celsius on its sunward face, while keeping the instruments behind it at room temperature. Since 2018, the probe has been making increasingly close passes through the sun's outer atmosphere. On December 24, 2024, it made its closest approach yet, swooping to within about 3.8 million miles of the solar surface, or roughly 1 million kilometers. The data it has been sending back is being analyzed right now in labs in Maryland and California and Germany and Japan by scientists trying to settle a question that has been open for 80 years. We do not have the final answer yet. That is the honest thing to say. We are closer than we have ever been. We have ruled out some bad ideas. We have refined some good ones. But the corona is still doing something that, on the face of it, breaks the rule that heat flows from hot to cold. And this matters for the question of why space is cold, in a way that is easy to miss. Because the sun's corona is enormously hot, hot enough to vaporize anything we know, and yet it is also incredibly thin. The corona's particles are so spread out that even though each individual particle is moving fast enough to count as millions of degrees, there are so few of them that the corona as a region holds very little total heat. A spacecraft flying through the corona would not melt the way you might expect. It might survive the trip, the way Parker Solar Probe is surviving it, because temperature, remember, is the average motion of particles. The particles in the corona are moving fast, but there are so few of them that the spacecraft is not actually getting hit very often. It is like the difference between being slapped once by a heavyweight boxer and being lightly tapped by 1,000 small children. The total energy might be similar. The damage is completely different. This is one of the strangest sentences in modern physics. You can pass through gas that is millions of degrees hot and not be hurt by it because the gas is too thin to really touch you. The vacuum of space and the corona of the sun are not as different as their numbers make them sound. Both are mostly nothing. There is more to this. We are about to look more carefully at exactly how much nothing is in the space around us, because the road between the sun and the earth is not really empty. It is just very, very, very close to empty. We keep saying space is empty. It is not exactly empty, it is just very, very thinly filled. If you took 1 cubic centimeter of the air in your room right now, a little box about the size of a sugar cube, that box would contain something like 10 million trillion molecules. That is a 1 followed by 19 zeros, all packed into a space smaller than your thumbnail. The air is dense. The air is a crowd. Now take that same sugar cube-sized box and lift it up into space just outside Earth's atmosphere, in the region where the International Space Station orbits. In that little box you would find, on average, somewhere around 100 million particles. That sounds like a lot. It is not. 100 million is a tiny number compared to 10 million trillion. The density has dropped by a factor of 100 trillion. The crowd is almost gone. Keep going. Move your box out past the moon, past the orbit of Mars, into the open space of the inner solar system. The density drops again. In the region of space that the solar wind flows through near Earth's orbit, there are about 5 particles in every cubic centimeter. 5, in a volume the size of a sugar cube. Where your living room would have 10 million trillion. That is what we mean by almost empty, not nothing, but so close to nothing that it is hard to picture. And here is the strange thing about those 5 particles. They are not slow. They are not cold in the everyday sense. They are flying outward from the sun at hundreds of kilometers per second, hot enough that if you measured each one's individual energy, you would call it tens or hundreds of thousands of degrees. The solar wind is, in a sense, very hot plasma, but there are 5 of them in a sugar cube. This is the paradox that confuses almost everyone the first time they meet it. The solar wind is hot. The space the solar wind is in is cold. Both of these statements are true at the same time, and they do not contradict each other. The temperature of a thin gas is about how fast each particle is moving. The total heat that the gas can deliver is about that speed multiplied by how many particles there are. If there are very few particles, even very fast ones, the total heat the gas can give you is small. Imagine you are standing in a field and a single golf ball flies past you at high speed. The ball is moving fast. It has a lot of kinetic energy by the standards of one small ball. But if it misses you, you feel nothing. Now imagine 100 golf balls flying past at the same speed, still mostly empty air, still very little chance of being hit. Now imagine 100 million golf balls, packed shoulder to shoulder, all flying at you. That would knock you down and probably kill you. The solar wind is more like the first picture. The particles are individually fast. The total number of them, in any given moment, in any given cubic centimeter, is so small that you can fly a spacecraft through them and barely notice. So we have a strange picture, almost a comedy of definitions. The space around the Earth contains a hot plasma. The space around the Earth is also extremely cold. Both statements are honest. They are just talking about different things. The plasma is hot in the sense that each particle in it is moving fast. The space is cold in the sense that anything you put into it, given long enough, will radiate more warmth away than it gains. This is the deep version of the title's answer. The sun is hot. The space the sun's energy crosses is cold, not because nothing energetic is in it, but because there is so little of anything in it that the total heat available to a passing object is tiny compared to the heat that object radiates away. It is a vacuum where the loudest things are also the rarest. A road full of fast-moving particles that are too far apart to add up to anything you can feel. And out beyond the solar wind, out past the heliosphere, in the truly deep space between stars, the density drops further still. There might be 1 particle per cubic centimeter, or less. The galaxy is full of regions where the gas is so thin that, by any human standard, it would be called the best vacuum that any human laboratory has ever produced. It would be the cleanest possible nothing. And yet, even there, in the cleanest nothing, the universe is not silent. There is something still arriving, something that has been arriving everywhere, in every direction, for nearly all of cosmic history. A faint background warmth that we did not know about for most of human history, and that, when we did finally find it, took 2 engineers in New Jersey years to believe was real. That is the next rung. The oldest light still arriving. Let your shoulders drop. We are walking into something quietly enormous. In 1964, 2 engineers at Bell Telephone Laboratories in Holmdel, New Jersey, were trying to use a large, horn-shaped radio antenna for satellite communications. Their names were Arno Penzias and Robert Wilson. The antenna was a strange-looking piece of equipment, shaped a little like a giant ice cream cone laid on its side, designed to pick up faint radio signals from satellites in low Earth orbit. Penzias and Wilson had a problem. Their antenna was picking up a low, steady hiss. Not loud, not dramatic, just a background fuzz that would not go away. They could point the antenna in any direction, at any time of day, in any season, and the hiss was always there, and almost the same level. They tried everything to get rid of it. They went out with brooms and shovels. They cleaned the antenna. They discovered that 2 pigeons had been nesting inside it and had left droppings on the surface. They cleaned the droppings off. They checked all the wiring. They eliminated every possible source of interference they could think of. The hiss remained. They started talking to other physicists. And word eventually reached a group at Princeton University led by a physicist named Robert Dicke, who had been doing theoretical work on what the universe might have looked like a long time ago. Dicke and his team had been calculating what the leftover light from the early universe should look like today, billions of years after it was first released. Their calculation predicted a very specific kind of glow, a glow that would fill all of space in every direction with no preferred location, a glow that would be at a particular temperature, just a few degrees above absolute zero, a glow that, on a radio antenna, would sound exactly like a steady, faint hiss. When the Princeton group heard about Penzias and Wilson's noise, they realized what the engineers had accidentally found. Penzias and Wilson had discovered the leftover heat of the Big Bang. That sentence is so strange that it should be slowed down and taken apart. The early universe, in its first hundreds of thousands of years, was a hot, dense soup of particles and radiation, glowing white-hot like the inside of a furnace. About 275,000 to 280,000 years after the universe began, the soup cooled enough that the particles and the radiation stopped interacting. The radiation flew free in every direction. It has been traveling ever since. That radiation is still arriving. Right now. Through every cubic centimeter of space, in every direction, all the time. The universe has been expanding for nearly 14 billion years, and as it expands, that ancient light has been stretched out to longer and longer wavelengths. It has cooled, on average, from the temperature of a furnace down to a temperature just barely above the coldest temperature physics allows. It is now at a temperature of 725 Kelvin, just under 3 degrees above absolute zero. Roughly 270 degrees below zero on the Celsius scale. That is what Penzias and Wilson found in their antenna. That is what their faint hiss was. The leftover light from when the universe was very young, now stretched and cooled to a temperature just above nothing. It fills everything. It is everywhere. There is no place you can go in the universe to get away from it. It is in your room right now, passing through the walls, passing through your body, faint and weak and pervasive. It is the deepest background of the cosmos. This is what we mean when we say space has a temperature. We mean the cosmic microwave background, the CMB, the ancient warmth that fills everything. We mean 725 Kelvin. That is the temperature any thermometer in the deepest part of space, far from any star, would eventually settle at. Not because the vacuum itself is warm, because the radiation passing through it is. Stop for a beat. Almost every cubic centimeter of the universe is being touched, right now, by light that was emitted when the universe was less than 1,000,000 years old. That light is still going. It has not finished its journey. We are inside it. Wherever you are, in your bed or in your chair, you are sitting in the leftover warmth of the early universe. It is not warmth you can feel. It is so faint that your skin will never notice it, but it is real. It is the warmest thing in deep space when there is no star nearby. It is the temperature below which space, on its own, cannot fall. Or so we thought, for a long time. Because it turns out there are places in the universe that have somehow managed to be colder than this floor. A few of them anyway. And the one that holds the current record is doing something that, when you understand it, sounds almost impossible. A cloud of gas in the constellation, Centaurus, has cooled itself below the cosmic background, below the floor that the universe set for itself. It is, by current measurement, the coldest place that has ever been found in nature. We are about to meet it. This is the last rung. In 1995, two astronomers, Raghavendra Sahai of NASA's Jet Propulsion Laboratory in Pasadena and Lars Archie Nyman of the European Southern Observatory, pointed a 15-meter radio telescope in the Atacama Desert of Chile at a small, faint object in the constellation Centaurus, about 5,000 light-years from Earth. The object was called the Boomerang Nebula. It had been spotted in the late 1970s by Australian astronomers who thought its faint, slightly curved shape looked like a thrown boomerang. From a distance, it looks unremarkable. A small smudge of light. A dying star with some gas around it. Up close, it is one of the strangest things in the known universe. Sahai and Nyman were measuring the temperature of the gas in the nebula. They were doing this by looking at how that gas absorbs the cosmic microwave background. Remember the cosmic microwave background, the leftover warmth of the Big Bang. 725 Kelvin. The temperature floor of empty space. They found something they did not expect. The gas in the Boomerang Nebula was not just cold, it was colder than the background. Their measurement put the temperature of the outer gas at about 1 Kelvin, just 1 degree above absolute zero, colder, somehow, than the radiation passing through it. This should not be possible by the simple picture we have built so far. We have said, all through this video, that anything you put in deep space will eventually settle at the temperature of the radiation hitting it. We've said that the cosmic microwave background is the universe's floor, the coldest, passive temperature anything can naturally reach. The Boomerang Nebula is sitting below the floor. How? The answer is one of the most beautiful applications of basic physics in modern astronomy. The Boomerang Nebula is doing the same thing your refrigerator does, but on a cosmic scale and entirely by accident. At the heart of the nebula is a dying star in the late stages of its life. The star is shedding its outer layers, blowing them away from itself in a powerful outflow. That outflow is moving fast, around 164 kilometers per second, which is unusually rapid, even for dying stars of this type. The gas is expanding outward into space at high speed, and as it expands, it cools. This is the principle that runs every air conditioner and every refrigerator on Earth. When a gas expands, it cools. When you spray an aerosol can, the can feels cold afterward because the gas inside expanded as it left. The Boomerang Nebula is doing the same thing on a scale you can see in the sky. It is a cosmic refrigerator, expanding for the better part of 1,500 years, cooling itself with every kilometer the gas travels outward. And it has cooled itself by this slow, patient expansion below the temperature of the radiation that fills the rest of the universe. This was not a thing astronomers expected to find. There had been theoretical predictions, including a 1990 paper by Sahai himself, that planetary nebulae in just the right phase of evolution could in principle drop below the CMB. But finding one and measuring it was different. The 1995 observation, published in the Astrophysical Journal Letters in 1997, was the first confirmation that a place in nature could really be colder than the universe's own background warmth. Sit with that sentence for a beat. There is a place in the sky, visible to the right telescope, where the gas is colder than space itself. Newer observations have continued to study this strange object. In the 2010s, the Atacama Large Millimeter Array, the powerful set of radio dishes in Chile that succeeded the older telescopes Sahai used in 1995, took much higher resolution images of the boomerang. The pictures showed a more complex structure than the original boomerang shape, more like a slow hourglass with gas streaming out in narrow lobes. The temperature measurements held. The outer regions are still around 1 Kelvin. The nebula is still the coldest natural place we have ever found. It will not stay that way forever. The expansion is slowing down as the energy of the original outflow gets spread across more and more space. In a few tens of thousands of years, the gas will become so thin that the cosmic microwave background will start to warm it back up. The nebula will eventually rejoin the universal floor. The reverse refrigerator will run out of gas to expand. But right now, today, as you are listening to this, there is a small cloud in the constellation Centaurus that has, for centuries, been cooling itself below the temperature of the universe. It is colder than the leftover warmth of the Big Bang. It is the coldest natural place measured so far. And the way it got there is something so ordinary you have done a smaller version of it yourself every time you have sprayed deodorant on a winter morning and felt the can grow cold in your hand. Gas expanded, gas cooled, just over a longer time scale and a larger volume, and through more years than every human civilization has lasted. That is the last rung. The coldest cold in nature is not in the deepest, emptiest part of space. It is inside a slow cosmic refrigerator that has been quietly cooling itself for 1,500 years by doing the same physics as your kitchen. All right, we have walked a long way. We started at a window in winter. We have ended at a nebula 5,000 light years away. Take a slow breath. Let the room come back into focus around you. The last move is a small one. It is the move where the title finally settles into place. Bring the thermometer back. The one we started with, floating outside the spacecraft, plus 250 on the side facing the sun, minus 250 on the side facing away. 500 degrees of difference across the width of a doorway. That picture has not changed. The numbers are still the numbers. But by now the picture means something different than it did at the beginning of this video. At the beginning, it looked like a paradox. How can two things so close together be at such wildly different temperatures, with nothing between them, no air, no insulation, no wall, just empty space? We have walked through the answer. Slowly. From the window in winter to the 3 roads heat can travel to the spacecraft to the moon, to what temperature actually is, to the strange heat above the sun's surface, to the density of nothing, to the oldest light, to the cloud that is cooled below the cosmos. Now look at the thermometer again. The sunlight side is hot because radiation, the one road heat can take across a vacuum, is delivering warmth to it. The shadow side is cold because that same road carries no warmth into it, and the side is quietly bleeding its own warmth out into the dark. The space between them is not in between hot and cold, because the space between them is not really a thing that can be hot or cold. It is mostly the absence of a thing. It is not a medium. It is a corridor. The energy passes through, and the things in sunlight are bright and warm, and the things in shadow are dim and cold, and what we called space is not the temperature of either of them. Space is the silence the energy travels through. Space is the empty road. This is what cold really means, at every scale we have looked at tonight. Cold is not a substance. Cold is what happens when warmth flows out of something faster than warmth flows in. Cold is the radiator on a spacecraft, glowing faintly in infrared, shedding heat into the dark sky. Cold is the lunar crater that has never seen the sun, slowly emptying itself of every photon it ever had. Cold is the thermometer in deep space, settling not to the temperature of the vacuum, but to the balance of light around it. Cold is the floor of 725 Kelvin, the leftover warmth of the early universe, which the rest of the cosmos has never quite stopped giving off. Cold is the Boomerang Nebula, expanding so patiently for 1,500 years that it has cooled itself below even that floor. None of these things contain cold. All of them are doing something. Losing warmth, failing to gain warmth, radiating, expanding, sitting in shadow. Cold is a verb more than it is a noun. It is the verb that describes warmth leaving. The sun is hot because the sun is full of fast-moving particles, packed densely, jiggling against each other in a way that releases enormous amounts of light. Space is cold because space between the sun and the things the sun warms is full of almost nothing at all. There is nothing for the warmth to move into. The warmth is just passing through. On its way to anywhere, there are particles to receive it. Hot is a crowd. Empty space has no crowd. That is most of it. And the rest, the small remainder that makes the picture complete, is the strange fact that even where there is no crowd, there is light. The light from the sun, near our part of the galaxy. The light from other stars, in places further out. The faint ancient light from the early universe in every direction, everywhere. Light is the only road. Light is the warmth in transit. And anything we put in space, in the long enough run, settles to the temperature that the light around it sets. Settle in for a moment. Let the cosmic picture quietly fade out. The thermometer, the spacecraft, the moon, the corona, the nebula. Let them go. Come back to where you are, the room, the chair, the bed, the faint warmth of your own hands, resting wherever they are resting. The lamp on the table, if there is one. The clock on the bedside table. The slow rise and fall of your breathing. Right now, in this room, your body is at about 37 degrees Celsius. The air around you is cooler. Your skin is, quietly, all the time, radiating warmth into the air, and the air is carrying that warmth away, and some of it is escaping through the window, out into the night, into the cold sky. That same warmth, slowed down by walls and windows and clothing, is doing the same thing your spacecraft was doing in space, losing heat to whatever cooler thing it can find. The only difference is that you are surrounded by a thick, comfortable atmosphere that softens the swing, and a soft, warm bed that slows the radiation, and a room that is well within the narrow band of temperatures where a body like yours can rest. Above all of that, far above your roof, The same vacuum the sun's light has been crossing for 93 million miles is still there, still empty, still not warming up, still letting the sunlight pass through it on the way to your morning. The sun is loud and the vacuum is quiet, and tonight, like every night, you are on the warm side of a wall of light that the cold cannot cross. And the cold, after everything, is not a thing at all. It is just the long, quiet space where the warmth has gone.